Okay, hi everybody. Thanks for having me.
I forgot something.
Sure.
You can say good. You can say hi.
So yeah, hi. I can talk while you're doing this.
Yes.
Yeah, I'm an assistant professor at the University of Washington. I do data viz. I do a lot with communicating uncertainty, also kind of storytelling and visualization, so sort of AI plus visualization plus HCI, human-computer interaction. Today I was going to talk about some work I've been doing on trying to basically help people better understand measurements using concrete re-expression strategies, and we're trying to automate this. So visualizations help people understand numbers, obviously, by giving them a nice representation. But another way to help people understand numbers is to give them mental imagery, and sometimes this is actually more important or an important first step before you visualize data. So for example, we often see physical measurements like length, height, volume, weight, etc. in news articles. And often readers struggle to understand how much these quantities actually refer to. So there are various reasons why they're hard to understand. So you might not know the unit well. So how much is a gallon perhaps is not familiar. You might not know the magnitude well. 34 million gallons is a lot. It's hard to grasp. And even the measure itself, like volume, might be something that you don't have to reason about in everyday life. So people struggle with understanding measurements. So if I were to ask you how much is 1,000 gallons, what would you think of? I'm guessing you would try to start thinking about objects that are kind of in the ballpark of what you think 1,000 gallons is. And people who study in psychology how people mentally represent measurements find that they're often thinking about a scale of measurement sort of anchored by familiar objects, so things that they're familiar with the scale of. Journalists and designers, I think, kind of know this or intuit it. And so often you'll see them when they're including measurements in news articles using these concrete re-expression strategies where they're kind of re-expressing a measurement in terms of familiar objects. So 34 gallons is about 1.5 times the volume of a wash tub, or 1,100 pounds is about 5 times the weight of the gas range in your kitchen. And so this seems very simple and concrete and direct, but it's actually hard to construct these and really get them right. And that's because the comparative object is really important. You have to kind of get the right object. It's not clear what makes for the right object. And so they go through this manual process where they have to think about objects in the world and their properties, find measurement data on the web, which may or may not be accurate, convert the multiplicative factor, so figure out, is that easy to understand? Can I tell someone that it's 20 gas ranges, or is that hard for them to grasp? And then find a way to present it to the reader. And so our work is really looking at whether we could support automatic generation of these measurement analogies and then visualize them and make them available to people. And we're going to do that by making use of publicly available object measurement data and focusing first on physical measurements like weight, height, length, and volume, because people encounter those a lot just in articles, et cetera. So we're going to build a database of measurements for objects that we think are familiar to people and then construct automated algorithms for those. And so to build the database, we have this kind of 3-stage process where first we're going to think about objects that have criteria that we think are good for re-expressing measurements. Then we'll obtain instances of those objects from various online sources, and then we'll make sure that the objects that we got instances for are in fact represented by those instances. So briefly walk you through this. So our first step really was trying to think about, well, what criteria should an object have to be sort of effective as a re-expression? And so one thing that's obvious is that if you're going to re-express physical measurements, you want concrete objects. They should have mass. They should take up space. You also want things, though, that are countable. So I could tell you 90 grams is equal to the weight of sand, but that's not very helpful because sand is ambiguous in its quantity. You also want them to be familiar. So you want objects that people not only recognize, like a hippo, but that they actually interact with in daily life, so they have a sense of the scale. And finally, you want objects that have low variance in the measure. So I could tell you 35 pounds is equal to the weight of a dog, but you don't know if I mean a big dog or a small dog. There's a lot of variance, and so we want things that don't vary that much. So once we had these criteria, we were able to go to semantic databases, namely WordNet, which is basically a graph of concepts, where the concepts are called synsets. They have a definition. A lot of them are objects, and you can sort of reason about the attributes that these objects have based on where they are in this WordNet graph. And so basically we looked at sort of the high-level nodes in this WordNet graph. We found that artifacts are defined as man-made objects that can be taken as a whole, and this sort of corresponds nicely with concrete countable objects. They have a clear quantity, and they're obviously concrete things. We also wanted things that were familiar, and so by using WordNet, we were able to also use a measure from a related database called ImageNet, which is basically an image-based version of WordNet that includes a measure of the popularity of these various objects in web corpora. So online, how often are they mentioned? And so we use that to kind of get rid of some unfamiliar objects, and so we're left with about 2,000 objects, or synsets as they're called. And so then what we can do is go out and gather measurement data. So we created kind of a pipeline to automatically extract measurement data from a few sources. One was Amazon, the product database, where they have a whole bunch of consumer goods, mostly things that fit in a box, but still a wide range of objects. And then we also use Wikipedia, which has a lot of objects across different scales where you can get measurement data in these little tables called info boxes in the articles. And so we queried basically with these adjective phrases for each synset or object representation. We used different strategies for each of these two sources, but basically we got a lot of instances of these objects where we have measurements for these things. And so that leaves us with about 25,000 instances of objects, and we are now down to about 1,300 object types or synsets. But as you might expect, we got a lot of false positives, so cases where it's not quite the object we intended. So if I put in a search on lighthouse in Amazon, it's going to give me things like cookie cutters, and so we had to filter some of that out. And so we have a last step, which is kind of filtering this database. We're using crowdsourcing, Mechanical Turk, which is a crowdsourcing platform, to do that. So we end up creating this database that has about 13,500 instances of about 1,200 objects. We've created web interfaces and an API for developers who want to just use this data directly. But again, our goal was to create automated sort of analogy or re-expression algorithms that we could then use on demand with visualizations of the results. And so we took this database and we started thinking about these re-expression strategies and how we could potentially automate those. So one that's really common is reunitization. And all three of these examples show reunitizations of 1,000 gallons, where you're basically re-expressing 1,000 gallons as a multiple of some more familiar object. And so we have all these objects in our database. We can try to then reason about, or we could create a reunitization for any of them, but then we have to sort of think about which is the best reunitization for this input. And so our goal is really to rank them. And so the way that we do that is basically defining kind of a function or an equation that's going to basically rank all of the objects in our database according to various criteria that we think are important for these re-expressions. So familiarity of the object is important. Variance in the object should be low, that's important. And then how easy to understand the multiplier is also important. So here in the top example, the multiplier is 8.9. Is that really an understandable number versus 2.4, et cetera? So just briefly kind of how we define these scores. You can think of each of these terms in the equation as a score for how good the object is on those in those ways. And so to get familiarity, we basically know from research in psychology that what is familiar depends on the specific magnitude. So you think of different objects depending on what measurement I give you. So we had a task that we had crowd workers do where we gave them a sample measurement and showed them a grid of objects and said what objects are familiar to re-express this measurement. So we basically get these kind of ranked objects according to the results of this task. We then looked at the actual distributions of measurement data and figured out which objects have low variance in the measure because we want to prioritize those. So these are two similar objects, an oven and a gas range, but gas ranges have less variance. Oven might include some really small things. And then finally, we're trying to score the different reunionizations based on how easy this multiplier is to understand. And we can look at psychology research that says that people have like a really good sort of precise notion of numbers 1 through 3. And then 4 through 10 are not too bad. But then as we move away from 1 or get higher than 10, our mental representation of numbers gets imprecise. We're just not very good. And so we can do all this and we can automatically, create these reunitizations. We get for 1,000 gallons 2.4 times the volume of a hot tub, et cetera. And so these use familiar objects. They seem okay, and we've evaluated them in multiple ways. But like I said, we were really excited kind of more about how we could apply this type of thing sort of in the world, and particularly in journalism where you'll see news articles. So we created these different interactive reader applications that will apply these re-expressions on demand and then express them using sort of simple visualizations. So here, someone clicks on this, they get the top 5 reunitizations from our algorithm, but we're creating these little bar charts. Basically, we're taking images of this object from ImageNet and setting a constant width so that you get these little bar chart type things that people can quickly scan and compare. We had another strategy that's sort of represented more as a number line, where we're going to look and take the top objects from our database using similar equations, but the ones that are sort of near the measurement that the person's clicked on, so you get a sense of objects that have measurements close to this. And then finally, we had a strategy where our visualization is not so sophisticated, but it's a proportional analogy where you click on multiple measurements and you get a pair of measurements that are that have the same ratio between their measurements. So here we could probably do fancier visualizations. I think it'd be fun to sort of design something to show that ratio better. So that's kind of what I have to share today. We have a bunch of stuff online, data, we have demos, and I also wanted to mention, if you like this type of visualization of measurement analogies, we have a browser plugin for a different project where we're making personalized maps for spatial measurements like distances and areas. So check that out if you're interested. Thanks.
Merci beaucoup, Jessica. On prend 2 minutes par conférencier si vous avez des questions à poser. On en a une ici déjà.
So
We can paraphrase.
what I wonder is there any research on whether an integer number is easier to understand than a fraction? Because
Yeah.
I wondered why you didn't just round to an integer.
Yeah.
Because lots of these measurements have an uncertainty, like not every
Yeah.
is this exactly the same.
Yeah. So.
Might as well just round.
So we do round. Actually, we have a rounding strategy. We sort of cap the rounding once we've lost more than like 5% precision with the actual measurement. So I think it's interesting to think about what people do with numbers. I think probably when you show them 2.4, they do round. Maybe they round to 2.5. But we figured it's better to let them round in their head than sort of round and lose precision in that way. There is research, there was actually research at the conference presented on how people do understand fractions like 0.5 or and maybe a quarter, et cetera. And so we looked at psychology research and we couldn't find anything reliable about like how people understand fractions or which fractions do people understand. So we didn't incorporate it, but I think there's now more recent research that we could use. But yeah, I think it's complicated to know kind of what people, I don't think people actually care about the decimal points all that much, but we show them because we don't want to like get rid of information. So thanks.
Yes, I assume you don't round when you're treating astronomical data or atomic emission data, because that is known very precisely. You make constraints on that?
So in this case, we don't have any astronomical stuff. We have, I mean, the biggest objects we have in our database are coming from Wikipedia, and so we have things like big bridges or huge buildings. I think we have like space stations, but we don't have anything, astronomical. And there, I mean, we're keeping track of significant digits in our database. Like, so we're getting the measurements, and then we're starting with like whatever a number of significant digits we have just from the data we collected itself. But
On va prendre une dernière question, je pense que Nicolas, oui.
Did you look at the sort of affinity between the reunit, I guess, the new unit and the original thing? Like 1,000 gallons seems to me it would be like a 10 by 10 by 10 cube of gallons of milk, like sort of liquid to liquid, or like.
We didn't have anything that would specifically say like liquid to liquid, but I think it comes out actually in this task that we had people do where we showed them a measurement and we said, what's a familiar object? And so when you show them like something like 100 gallons, they're more likely, I think, to say that the objects that are familiar are things that I think of as having volume. And so I think it comes through in that way. But yeah, I think you do want to kind of match sometimes like you want things that hold water or whatever, or milk, et cetera. And so we wouldn't have one that's like 1,000 gallons of milk because we're trying to cap the multiplier, or we're trying to minimize the multiplier, keep it in this range really. So But yeah, I think there's lots of ways you could expand this to kind of be more sophisticated. I think it's hard to know exactly how people deal with measurements, but yeah, this was a kind of first stage attempt.
Thank you so much.
Thank you.
On garde le rythme assez rapide, hein, aujourd'hui.